Okay, so I think we are good to go with this. So today we will start chapter 13, which is equilibrium and human movement. And we will be quantifying torques, but from a human body and human movement point of view. And we will learn about something called the levers in the human body and the classes of these levers. And we will look at also something called the mechanical advantage and how that is important for us and its relationship with levers, and they will talk about leveraging the human body movement and the base of support and stability and balance. So that's my plan for today. A lot of information that will help us actually move forward in this chapter. So let's do this. Start with this. So I will start with the torque. So how would you define torque? Yes, it's the tendency to rotate, right? And because our body is a multi-segment coupled pendulum system, we have a lot of joints, all our segments tend to rotate, right? And what is the thing or the tissue that is generating rotation? Muscles. And muscles are attached to bone, right? And bones are the levers actually with the muscles and the joints, and that's what we're going to be learning today. So rotary effect of a force about an axis of rotation, that's our joints in our biomechanics, and it is actually measured as the product of the force and the force moment arm. Remember that we will multiply the force multiplied by the distance, as long as the distance, it's the perpendicular force multiplied by the distance. So torque is moment, that's what you learn in statics and dynamics, and we try to avoid moment because we have momentum, but that's force multiplied by velocity. So the most important thing is that you're going to multiply force with the distance, but the force need to be perpendicular to the line of action. So the distance need to be perpendicular to the line of action of the force. We good with this? Okay. Now, if you look at this, so let's say this is a door, and which position of the force application will be good to opening the swinging door? So this is the joint, that's the force, and that's the distance, right? So this is our perpendicular distance, that's the line of action of the force, right? And that's the joint. So which one will be, which of these schematic will represent an easier way to open the door? Because you have the larger distance, correct? And when you multiply the larger distance with the force, you get a larger torque, which is a larger tendency to rotate. Make sense? We good? All right. We're all good with this. Now here's the tricky part. The moment arm of the force is the perpendicular distance from the force line of action to the axis of rotation. So let me show you something. The example that we looked at before, we have, this is the distance, right? And that's the force, and the distance is perpendicular to the line of action. Do you agree? Right? That's how it looked like. Now for the second schematic, see that the force is coming with an angle. So what is going to happen? You need to resolve the force into a vertical component and into a horizontal component. See that? Now the horizontal component, it is passing through the line of the rotation, the angle, so the joint, the fulcrum, where the rotation will take. Anything that is passing through the line, the joint or the rotation point, that's zero. So the only one that is generating the rotation is the perpendicular force. Does that make sense? Because that's the one that is perpendicular to the moment arm. Now, let me ask you a question. So if I told you that this force here has an angle of, let's say, 30 degrees, and the force is 10 newtons, right? And the distance from here to there, to this point, is 3 meters. How much is the torque? You have a 10 Newton force with an angle of 30 degrees, right? 30 degrees, make it small. And you have a distance of 3 meters. How much is your torque? I'll give you a couple of minutes. Yes. And always counterclockwise is positive, right? In the torque. Okay. Any values, numbers? 5 newtons? Okay, so let's do this. So this force needs to be resolved into a horizontal and vertical. Now, the horizontal one is 10 cosine 30, right? Because that's between the two, between the line of action and the force. Now, this one here, the vertical one, is going to be 10 sine 30. Do you agree? Now, the 10 cosine 30, it's passing through the joint, right? Rotation. So the distance is 0. So we don't care about this one. So we erase this. That's not going to help us. The only one that matters is 10 sine 30. And you multiply, that's the vertical and perpendicular to the line of action of the moment arm. So you multiply 10 sine 30 multiplied by 3 meters. How much is that? There you go. 55.0. No, it's 10, 1, 5. 10 sine 30 is half, and that's 5, 15, Now, what is that? So let me just write it correctly. So you will have your torque equals 10 sine 30 multiplied by the distance, which is 3. That is 15. What is the unit? Newton meters. Don't forget the dot, right? Because that's how it should be. So if you have a force with an angle, you need to resolve it into the x and y component, and then find the distance, and then you multiply these two. The one that is perpendicular to the moment arm is the force that matters. Make sense? We good? Okay. Now, where do torques occurs within the human body? As I mentioned, muscles create tension. That's force, and the muscle moment arm is the distance between the muscle attachment and the joint where rotation takes place, and that's the joint where crossed by the muscle is where we have the rotation. And we would like to take a look into this and understand how we would like to analyze the torques in the human body produced by muscles. So here's the thing. See, this is our elbow joint, and that's the biceps muscle connected to the bone, the forearm. And see the distance, the perpendicular distance between the rotation, that's the joint, and the center of rotation, and that's the force. So if you have, let's say, I'm doing 90-degree with my forearm and upper arm, that is going to show us the distance, the rotation, center of rotation, and where the force is coming. Now, the muscle moment arm is at maximum at 90-degree angle of pull. See here, it's 90-degree, that's the maximum distance. Now, if you change the pull, the arm away from the 90 degrees in either direction, doing flexion or extension, both ways, your moment arm will be smaller, right? That means the largest torque can be created when we have a 90-degree angle of the upper arm and the lower arm. Does it make sense? And if you look here, see the distance? The D is larger here than this one there, than this one here. Okay, now there's another way to look at this. You can look at it in the other direction. You can say, well, okay, I don't want to look at this distance, but if I would like to find the torque, here, the torque is maximum here, right? That's max. That is smaller torques here in this one in this position. Now, what happens is that if you say, well, okay, I'm going to stick with this distance. I want to stick with that distance, the one that we started with at the beginning. In order to do this distance or to use it, you need to resolve the force into vertical and horizontal. So you will say that this is the force in the vertical one, and that's the horizontal force. And the force is smaller from the one on the top, even though the distance is the same, but the force is smaller, which means that the torque is smaller, right? And we're going to look at examples. So let's do this here. Let us look at this example. And what I want from you is to solve it on your NFP. We would like to, okay guys, so let's say we have this. Two children sit on opposite sides of a playground seesaw. If Joy weighs 200 newtons and is located 1.5 meters from the seesaw axis of rotation, and Susie weighing 190 newtons and located 1.6 meters from the axis of rotation, which end of the seesaw will drop? And so that is a torque example. And what I want from you is to draw the free body diagram first before we do the analysis. You have forces, which are weights going down, and you have distances, and you know that the torque or the tendency to rotate is in the clockwise is negative, counterclockwise is positive. So you have subjects, weights should go down. So this is the weight down for the first one, and that's the weight for the second one. And you have the distances, and the torque counterclockwise is positive. So where do you think which one will drop? And in these examples, you always need to have the free body diagram, right? And look, the moment arm is perpendicular to the line of action of the force. So you don't have to resolve because you have a 90-degree angle between the two, right? So a simple multiplication, that's all what you need. You have value? Which one? So that is correct. So what you do is actually you say, well, no, yeah. So what do you say is that, well, this tendency, remember, anything in the human body now is torque. So we don't want to work with forces. So what happened is that this torque for Joey is going to be negative, right? Because it's clockwise, and it's 200 multiplied by the distance, which is 1.5, and that is 300 negative Newton meters. We good? On the other side, this rotation, this is our arm, and the rotation is going to be like this, so it's going to be counterclockwise. So that's positive. So the torque of Susie S is going to be positive 190 multiplied by the distance, which is 1.6, and that's 300. How much? 304, and that's Newton meters. So you can see that this is going to be winning on that side in the rotation. Does it make sense? But always make sure that you know the direction of the rotation. So you can say, well, Susie's side will go down, or you'll say that we will have a torque in the positive direction, and its torque is of 4 newtons meter, right? And this is how you're looking at the example. So the difference between the two is 4, and that's positive, and that's Susie's. So resultant torque is positive direction, and Susie's end of the seesaw will fall. Make sense? Good? And that's something to keep in mind when we look at the directions, because that's important. Now, where is this also helpful for us in biomechanics, especially for athletes? The larger the moment arm, the larger the torque, correct? And again, torque is like a force. So one of the important things that people do, for example, skilled pitchers often maximize the length of the moment arm, and that's human body configuration between the hand and the total body axis of rotation, and during the delivery of a pitch to maximize the effect of the torque produced by the muscles. Does that make sense? And that's why when you look at people who play sports, you see them that they go as far as possible, and their body is the axis of rotation just to maximize that. Make sense? Yes. So that's from a biomechanics point of view. Also, dancers, actually, when they would like to do rotation, remember, their movement is rotation. If they want to maximize that, remember if we have something called couple moment? So if you're driving and you're holding the car steering, your one direction is up and the other down, and the force going up and the force going down should be equal, right? So because they're equal, this couple moment, how would you calculate the couple? What is the couple moment? You take one force, right, and you multiply it by the distance between the two. That's the couple moment, right? That's all we need to do. It's not the two forces, it's just one of them, and you multiply it by the distance between the two. And that's what dancers actually do when they do their routines. So what they have to do, see, this is the left and right feet, and what the distance between them. So one of the forces is in the one direction, the other force in the opposite direction. All what you need to do, take one force and multiply it by the distance between the two. So if they want to increase their rotation, so what do? They just spread their feet away, similar to the distance or the shoulder distance. That's the maximum actually rotation, because they would like to use them base of support. If you have your feet closer to each other, you're going to get smaller torque, right? So the difference between this one here and that one is this coupled torque is smaller than this one, because the distance is smaller, right? And the distance between the two, to make sure that it's coupled, that should be 90 degrees and that should be 90 degrees. So the closer the closer the feet are together, the smaller the couple moment, and the smaller the torque that is generated. Now, if a dancer wants to move on one foot, the distance between the larger the foot, actually the larger the moment, the force. And that's something important when people are selecting dancers in ballet. They pay a big attention into the size of the feet. So the wider a dancer stands, the greater the moment arm. That's the stance, how wide the feet are away from each other. And if even two dancers holding each other hands and on one foot, they actually increase the moment arm, and that creates more moments for them. So the greater the moment arm for the force couple generated by the feet when a turn is executed, that's the couple moment. With a single foot stance, the moment arm is the distance between the support point of the foot, closer to the toes and to the heel. We're good? So these are examples of how important torque actually in biomechanics. And one of the things that we will be talking about, remember, we focus on ACL tears, and even that actually we'll see that affects the ACL tear. It's a risk factor for ACL tears, because you're generating more moment that is rotation on the knee, and that can create actually problems for us. Does it make sense how we look at that? Okay, now torques the torques required at the hip, knee, and ankle during cycling are influenced by body position and cycle dimensions. That's another thing actually in biomechanics and the sports, that the design of the cycles, it's a biomechanical problem. So that's a biomedical engineering actually issue, problem for us to work with. Now, so we've looked at the torques. Now, we would like to take the torques into the next level and look at levers, because those are very important in the human body. Remember, we have muscles generating force, we have bone act as levers, and then we have joints that like the center of rotation. Make sense? So what do we do? So what is a lever? It's a simple machine, right? It's a machine consisting of relatively rigid bar-like body that can be made to rotate about an axis or a fulcrum. And there are first, second, and third class levers. If you would like to guess, in the human body, which is the most class of levers, dominant class of levers? Just a guess. Have you heard this before? Class 1, 2, 3, third. Most of our joints and body actions are third class. And I will show you what does that mean. But before we go there, here's the thing. This is a lever. They've probably seen this in physics or statics. So, and I'm showing the relative location of the applied force, the resistance, and the fulcrum, which is the axis of rotation. And the location of these three, indicates what class of lever we have, and would determine the lever classification. So here's the thing. If our center of rotation or fulcrum is between the force and the resistance, so usually the resistance is the load. So if I'm holding, let's say, a dumbbell, that's a resistance, right? That's the weight. So if the center of rotation is in the middle, that's class 1. If the resistance is between the force and the center of rotation, that's class 2. If the force is between the resistance and the center of rotation, that's class 3. And let me show you examples. So here, the first row, the top, this is class 1 levers, right? Why? If you have the center of rotation in the middle between the force and the resistance, that's class 1. So that's the center of rotation, force, and the resistance. So yeah, the boy is trying to pull the girl up into the air. Now here, in the scissor, you have two forces. This is your center of rotation, and you usually try to move these two sides of the scissor. So those are the resistance. So the center of rotation is in the middle. Here, this is the rock, this is the center of rotation, and this is the force you're trying to move. So that's class 1. Do we agree? We good with that? Class 2, if you are pulling, a load of dirt, so this is the wheel is your center of rotation because you're pulling up and down. Your resistance is in the middle, and the force is on the side. So that's class 2. Same thing goes with wrench that you would like to use to really, loosen a wheel. That's your force. Resistance is in the middle, and then the center of rotation is the A. On the side, very, very small differences between them. Also, same thing here. You have the force. This is what do you call the cracking? What do you call this? Not cracker. So you have the force and the resistance in the middle, and the center of rotation is A on the side. Make sense? We go to class 2. Class 3, the force is in the middle, right? So here we have the resistance, the force you're pulling, and you're trying to rotate around this point, correct? Right? Here again, that's resistance. You're pulling up, and then you're trying to rotate it this way. And now for muscles, for the body, this is your center of rotation. That's the force pulling up, and this is the weight pulling down. So the force is between the center of rotation and the resistance. Does it make sense? So that's class 3. Now this one here is actually most of our human body structure is designed as class 3. But I will show you class 2 as well as an example. Class 1, are we good? Section A, section B, class 2, and then we have the third class, which is what's dominant, what's common in the human body. Are we good? Okay. Now, example. So let's see if you can do this. How much force must be produced by the biceps brachii attaching a 90 degrees to the radius of 3 centimeters from the center of rotation? Remember, you need to have everything in meters, right? Because you're doing newtons. And to support a 70 Newton held in the hand. And remember, that means that the moment, if you are at equilibrium, it means the summation of moments is equal to 0. Does it make sense? So try to solve this, and I'll give you a couple of minutes. The distance is 3. This is your center of rotation. You have 3 centimeters here, and you have 30 centimeters there. That force is unknown. I know that this is 70 Newton going down. So how would you find them? How much force the biceps need to create in order to have that at equilibrium, which means balanced? So this is another way for us to assess the strength of muscles, right? So you can bring weights and you can hold them, and you can find how much force your biceps are creating, and you keep increasing the weights as long as you're holding it and with the distances. So that's 3 centimeters. That's the normal anatomical actually distance between our attachments between the center of rotation and where it's attached on the bone. So that 3 centimeters is really, really an important number. And then your arm length, for arm length, will decide how much you can actually hold. And that can give you how strong is your biceps. So that's an indirect measurement of the strength of the biceps. Any numbers? We good? 700? So how will you do this? So what you need to do is you will say, well, if this is at equilibrium, the summation of torques should equals to 0, right? Because that's at equilibrium. Now, we assume counterclockwise to be positive. So what you do will say, okay, this force, see this, the force that unknown, the tendency to rotate this is the distance between the force, line of action, and the center of rotation. So this is going to be rotating this way, right? So that's positive. So what do? You'll say, well, Fm multiplied by, how much is the distance? 3 centimeters. In meters, how much is that? It's 0.03, right? Now, so that's equal to 0, right? 0 equals, that's positive. Now the other force, this is the line of action, and that's the moment arm. So the force is going down, so that's going to rotate this way. So that's clockwise, that's negative. So we'll say minus 70 multiplied by the distance between the line of action and the center of rotation, 30 centimeters, which is 0.3 meters, right? 0.3 should equal to 0. Now, move one side, one of those, this is negative. If you move it to the other side, it will be positive, right? So you will have 70 multiplied by 0.3. How much is that? That's 0.3 equals Fm, that's unknown, multiplied by 0.03. So that's going to be 7, that's 21, equals Fm multiplied by 0.3. Divide each side by 0.03, sorry, right? 0.03, that the force is going to be 700. That's your force. Make sense? So that's how we use actually the torque in analyzing the human motion. So that means that the biceps need to create 700 newtons in order to balance a 70 newton ball. Does it make sense? So that's a lot of force actually to be balanced because the moment arm is large. So that is here. That's another, representation of how did we solved it. Summation of torques around E. E is the center of rotation, right? Around that point should equal to 0. It's at equilibrium. Fm multiplied by the dm, that's positive because it's counterclockwise, minus the weight, which is Newton, multiplied by the distance, which is 70 by that 0.3. And then you get the Fm, and we're all good to go with that. Does it make sense? Okay, another example. Take 2 minutes, and two individuals apply force at opposite sides of the frictionless swinging door. If A applies 30 newtons at a 40 degrees angle, 45 centimeters from the door hinge, and B applies a force at 90 degree angle, 38 centimeters from the door hinge, what amount of force is applied by B if the door remains at static position? And remember, we have angles, so be careful about the angles now. So let's see how much force B should be applying in order to have the door at equilibrium, which means it's not moving. We have numbers, good? 20.8. So how would you do this? So let's first remember, we have a force with an angle. You need to resolve that angle, correct? So, and because I would like to have the perpendicular force, which is, with the moment arm. So here's what we're going to do. I will start by saying, well, okay, this force, Fa, need to be resolved into a vertical force going down, and we have a horizontal force going this way. So that's good. Now, the 40 degrees is between the Fa and the horizontal one, right? That's going to be Fa, right? Cosine 40. Do we need this one? No, because it's passing through the center of rotation. The distance is 0. That's gone. We don't need that. Now, the other one, it's Fa sine 40. That's the one that we need, correct? And then you will do the summation of moments or torques should equal to 0. And our positive is counterclockwise. Make sense? So what do? You say, because that's at equilibrium. So 0 equals, Fa is going to be this way, rotating. That is clockwise, which means that's negative. Make sense? So minus, how much is Fa? Is 30 multiplied by sine 40, don't forget that, multiplied by the distance. How much is the distance between Fa and the center of rotation? 0.45 meters, right? So you put 0.45 meters. We good with this one? Now, the other force is Fb, and Fb is going to rotate counterclockwise, so that's positive, plus Fb. I don't know what Fb is, correct? But I know the distance is 0.38, so Fb multiplied by 0.38. We good, Hayden? Make sense? We good? Now, this is going to be negative, so you can move it to the other side. So you can, and Fb can stay alone. So you can say 0.38 Fb equals, how much is this multiplication? 30 multiplied by sine 40 multiplied by 0.45. 8.678. Make sense? Do you agree? Divide every side by 0.38. This is gone. How much is Fb? 22.8 newtons. Yep, that's it. We're using equilibrium and we're using the torques to solve the problem. Does that make sense? Here's the key point. Make sure that your force is perpendicular to the line, to the moment arm. If it's not perpendicular, resolve it into a horizontal and a vertical component to do this. And if you look at the solution, that's the key solution. Summation of forces around H, which is the moment, the center of rotation, equal to 0. we do the numbers similar to what we did, and we go. Make sure that your the notation for rotation is also followed. Counterclockwise is positive, always. We good? Any questions about the torque? Now, we have something called mechanical advantage. And the mechanical advantage is, from its name, is that you would like to take advantage of the mechanical setup so you can generate more force. Make sense? So let me give you an example. Let's say there is a big rock in the backyard and you want to move the rock from its place. You get, I don't know what you call it, a rod or a metal, rod, and then you put a small rock close by the big one, and you make it as a center of rotation, and you try to push it out, correct? Now, do you put that small rock close or far away from the big one? So if you said, well, I have a big rock here, I need to move it, that's my rod, do I put the small center of rotation here, or I put it far away? Which one is going to give us more mechanical advantage? The closer, right? Because you are going to leverage that moment arm and you multiply it by the distance with the force to create larger torque. Make sense? So the ratio of the moment arm of the force, or the force arm, to the moment arm of the resistance for a given lever is actually the mechanical advantage. So you need that ratio. Do you need the ratio to be larger or smaller? Larger, right? So the larger this moment arm, the larger this distance, the better. And remember, it's the force arm divided by the resistance arm, right? That's not English. Yeah. So this one and that one. So if this is 6 and that's 1, that's good, correct? That's 6 over 1. But if it was the other way around, your mechanical advantage will be smaller, right? So if this is 3 and 2, now you have 3 over 2, so your mechanical advantage is smaller, lower. That's not what we want to do. Now you look at this here. Do you think this is at equilibrium? If you look, 10 multiplied by 2, that's 20, and 20 multiplied by 1, that's 20, that's at equilibrium. Even though that you are pushing with a smaller force. So the larger this arm, the larger the mechanical advantage that you are getting in levers. So a force can balance a larger resistance when the force arm is longer than the resistance arm. There's another thing. You can also, with a smaller distance, a force can move a resistance through a larger range of motion. That's D. That's a different thing. When the motion with a shorter than the resistance arm. And that's what I told you when we have this big rock and small rock, that you will get it to move larger forces. Now for the human body, remember we said most levers with the human body are examples of third class levers, and those are examples. So the biceps, we took this. This is your resistance. So let's say there is a weight pushing down, that's R, and you have the force, and that's the center of rotation. So the force is in between the center of rotation and resistance, class 3. We're good. Also with the knee. So the knee, this is the center of rotation, and you have the force of the patellar tendon on the knee, and you have the resistance, which is the weight pushing you down. Does it make sense for the knee? And also for the medial deltoid at the shoulder, this is the center of rotation, that's the force, and that's the resistance. So most of the levers in the human body are actually class 3 levers. And that's important when you look at the analysis. Now remember, do you remember these? Concentric. What is concentric? Shortening of the muscle. Now eccentric, let's say I have a weight and the weight is too heavy, it's pulling my hand down, I'm trying to slow it down, that's eccentric. Does that make sense? So it's not shortening, it's elongating, but I'm trying to push to slow it down, that's eccentric. And then isometric is no change in the length, that our contraction. Now what happens is that if you have eccentric contraction, this is an example of class 2. So let's say I have a weight and the weight is dropping down, right? It's going down. So that is the force pulling down, right? And I'm trying to pull back resistance. So the resistance now is the middle between the force and the center of rotation. That's an example of class 2 in the body. But usually, normally, we have class 3 levers in the body. So the elbow flexors contract eccentrically to apply a braking resistance and control movement speed during the elbow phase of curl exercise. It's an example of a second class lever. Good with that? All right. Now we have something important to take in consideration about the elbow, because of remember the resolving the forces into horizontal and vertical. Your elbow could be subject to stability, or it could be subject to dislocation. So if you have flexion extension that's larger than 90 degrees, if you have your biceps pulling up, we are trying to resolve into this direction and that direction, correct? So what is this doing to the muscle? If you are pushing in that direction, you are pushing your forearm into the joint. That's stabilizing the joint, right? But if it's like this, and you try to pull to do the hard flexion, you're actually dislocating the joint. And I've seen this. I've seen people actually, without holding anything, they're trying to do this, they dislocate their elbow because their muscle is so strong, because they do bodybuilding and all of these things, even the slightest movement can dislocate their elbow. So you need to be careful actually with these. So that's called dislocating component, and that's the rotary component. This is the rotary component, and that's stabilizing component. So contracting of the biceps brachii produce a component of force that at the elbow that may be stabilizing or dislocating depending on the geometry or the configuration of the upper and lower arms, depending on the angle present at the elbow when contracting occurs. Does that make sense? You good with that? So here, so what's happened with this one? If you have this force like this, so you have a force pulling that way and a component pulling this way, right? That's going to rotate. What's this going to happen? Dislocate. It will take this away from the upper arm. If the angle is, more than 90, that's what's going to happen. This one is going to be, so that's the force. You will have a component going up and a component go this way. That's stabilizing because that's pushing it into the joint, from the joint. Yep, that's correct. And that happens only if you have an angle, right? If you're less than 90. If it's at 90 degrees, that's the maximum force moment, maximum rotation, and no dislocating or stabilizing, because you don't have any other components in the horizontal axis. Make sense? No, if the angle of the elbow is smaller than 90, dislocating. If it's larger than 90, that is stabilizing. So muscle force can be resolved into rotary and dislocating components, or stabilizing components. That's how rotary, that's for sure. But we have a stabilizing or dislocating component, right? And that's the thing actually, I don't know if you know, in martial arts, so when people do this in martial arts for someone else and they actually flip, because the body doesn't want to dislocate the joint. So if you do this with someone, you're dislocating their elbow because it's coming out from its location. Okay, static equilibrium. Remember static equilibrium? That's one that we talked the summation of torques equal to 0, but also summation of forces in the x-axis should equal to 0 and summation of forces in the y-axis should equal to 0. That's we learned in statics, right? And the condition summation of forces vertically should equal to 0, summation of forces horizontally equal to 0, and summation of torques equal to 0. Now there is another concept that's important, and that's called dynamic equilibrium. And that's an important concept. So we have now acceleration. Remember, summation of forces equal to 0 and torques equal to 0. Now we have acceleration. Now here's a question to you. If I told you summation of forces equals mass times acceleration, we've seen this before, right? Now the force. So what happened with the torques? Summation of torques should equals what? What is the thing that is a reciprocal or something that mimics mass and rotation? So if you're looking at linear kinetics, we're talking about masses. If we are looking at something that is rotating, what is the thing that should be representing mass? What is the thing that will prevent? So mass prevents things from moving. Inertia. It's I, right? Inertia. And instead of acceleration, what we do angular acceleration, right? So the summation of forces equal to 0, that's static equilibrium. Summation of forces equals mass times acceleration, that is dynamic equilibrium, if it's equilibrium. And if it's torques, you multiply the inertia with the angular acceleration. Make sense? So here, bodies in motion are considered to be in a static equilibrium, static state of dynamic equilibrium. It's not static, it's dynamic equilibrium, with all acting forces resulting in an equal and opposite direction inertial force. This general concept was first identified by a French mathematician, D'Alembert, and that's called D'Alembert principle. And dynamic equilibrium, the equations of dynamic equilibrium are summation of forces minus mass times acceleration in the vertical axis on the x-axis equal to 0, or summation of forces in the y-axis minus mass times acceleration y equal to 0, and summation of torques minus inertia multiplied by angular acceleration equal to 0. Let me show you an example. So let's say we have a subject a skydiver, and he is 580 newtons and in a free fall, but instead of acceleration 9.81, we have air resistance, right? So the acceleration down is 8.8 now. It's not 9.8. And because of force of air resistance, how much drag force is acting on the skydiver if we're assuming that the skydiver in a dynamic equilibrium, right? So how much force, drag force? Now drag force is resistance force. It's pulling in the other direction. And we're moving only in the vertical direction, in the vertical axis, in the y-axis. So that's another thing that you would like to look at, summation of forces. We don't have moment, so nothing is rotating, right? So just summation of forces in the y-axis should equal to mass multiplied by the acceleration in the y-axis if we are at dynamic equilibrium. Yeah, so how would you think about it? So what does that dynamic equilibrium mean? It means that this guy is hanging in the air. He stopped there. It's dynamic equilibrium. You know when the skydiver stops in mid-air when you look at this? So now how much drag force is generated to keep them in that position? And we're calling it drag because it's aerodynamics. And we're going to come to that later on in another chapter. Do you know how did we get the mass? You have the 580 newtons, that's the weight. You divide it, so F equals minus m times acceleration. Divide by 9.81, it will give you how much mass the subject is in kilograms, because we needed to multiply it with the acceleration. Do we have a number? 0.7? Okay, so here's what we're going to do. That's correct. So what you do is you say, well, okay, summation of forces in the y-axis minus summation, the mass multiplied by the acceleration on the y-axis equals to 0, right? So what do I have forces? I have the 500 newton, so that up is positive, right, for forces. So what I will say, minus 580, that's going down. That's the subject weight, correct? Now, plus F drag, because F drag is going up, right? It's pulling the subject up. So you have down and up, minus. How much is mass? That's the mass, which is the 580 multiplied by 9.81, because that's how you get the weight. You say that's 59 multiplied by 1,2, and you multiply it by minus 8.8. That's the acceleration in the y-axis because of the resistance. And you say that's 8.8. And you say that this is minus because it's going down, correct? Equals to 0. So you can move all the negative to the other side and keep F on the one side. So the FD here equals to 580 plus the 59.12 multiplied by 8.8. Does that check? So, and you will get 59.7 newtons. So the drag force, the air is lifting the subject by 59.7 newtons in order to keep 580 newtons going, floating in mid-air. See how big the effect of air resistance actually up on us. And that's an example of, this is called dynamic equilibrium because of drag. And we're going to learn a lot about this when we deal with what being in water, because air is a fluid, right? Did I miss anything with this one? Does this should be negative? Oh, I think this should be negative. So let me look at this. So that's minus 580. That's correct. No, we did it correctly. Now, minus and minus will be positive. You move it to the other side, will be negative. That's correct. Yes. So, but we need to have it minus the acceleration, and then you should be okay. Minus, that's positive. Move it to the other side, that's negative. That's my bad. Thank you. It's good. You got that. That's 59.7. Are we good with this? Yeah, I think this is a good place to stop here. And I will create a Dropbox for you guys to upload your work. And we will continue this lecture next time. Yeah, let me stop.